Hey robot makers, hope you're having a good day so far. So do you want to learn all about reed switches and Hall effect sensors and how to use them in your projects? Then this is the show for you. So let's dive straight in. My name is Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Okay, let's get over to the magic of magnets today. So yes, we're going to be using reed switches, Hall effect sensors, and some magnets. I've even 3D printed a cartoon style magnet. Why are they always that shape? I want to know. That's kind of horseshoe shape. Apparently it's to do with it's quite an effective way of what's the word? Forcing, combining, focusing. That's the word I was looking for. Focusing the beam. Cool. So yes, we're going to be looking at reed switches. If you've not looked at reed switches before, they're used in all kinds of things. Probably not as much nowadays, but they're kind of like a little glass capsule. I've got one here between my fingers. I'll show you this really close up on the screen. In fact, let's go full screen for a second. Let's see if I can get this on camera. So you can see there's like a little glass capsule. If I try and rotate this between my fingers, you can see that there's two pieces of metal that overlap, kind of like that, inside this little glass capsule. And the Hall effect sensors are just these little black components. We'll have a look at those in a bit more detail in a second as well. Okay, let's get back over to the slides there. So both of these use magnets to sense magnets. Both of these components use magnets to activate the switches. Hall effect sensors are slightly different than the more traditional reed switches, and they both have different kind of use cases. You can see there the reed switch has got these two overlapping reed blades. There's a gap between them. Now they can be normally open or normally closed. Normally closed, if the magnet comes close, they'll be forced apart, whereas they normally open, they're open like that, and when the magnet comes near, they will close. So there's that bit of an overlap between the two pieces of metal, and there's an inert gas, usually nitrogen, I believe, inside these little capsules, and there's a little glass capsule surrounding the whole thing. So they're quite complicated, I assume, to produce, whereas the Hall effect sensors are completely electronic. So there's we'll have a look at how they work inside as well in a second. So what is a reed switch? See, I zoomed in on my breadboard there. There's all kinds of gunk and things in between the components there, but this is a much more zoomed in view, and you can clearly see those two reed blades there. So they're a very simple magnetic switch invented in 1936, so nearly 100 years old next decade. Two ferromagnetic metal reeds in a glass tube. The reed touches when the magnetic field is present, and they're hermetically sealed, so there's no oxidization. Those they're not going to basically corrode over time. There's no power required to operate them, so this is a really good use if you want something that's very low power, and that simply when they touch together it completes a circuit. So it's a bit like an on-off button, but it's activated by a magnet. So the fact that they don't need any power is really, really cool. So how do they work? Let's have a look at this in a bit more detail. So yes, reeds are normally separated, normally open. The magnet brings the reeds together. When they touch, completes the circuit, and we can detect that with some very simple code. Or if we're doing this in an analog kind of circuit, it will just complete the circuit. So very, very simple to use in any of your projects. So yeah, when the contacts close, the current will flow, the magnet is removed, they'll just separate again. That's one of the other cool things about them. They don't get stuck together, they will separate again. So how close do we need the magnets to be? We can experiment with that in a bit of a demo in a minute or two, which is why I've created this 3D printed magnet that's got two, is it neodymium magnets? I always thought it was neodymium. I don't know where the extra S came from in my thoughts, but yeah, neodymium rare earth magnets. They're a bit too powerful, to be fair, on reed switches, but that's kind of what you can get hold of if you search for magnets on Amazon. I bought a whole bunch of these. There's a whole bag load of little magnets in there. So yeah, we'll have a look at a demo in a second that uses those. So what kind of applications of reed switches? So door and window sensors for security systems, they typically use these. That's why there's two cables that come out. When the other part comes near it, it will complete the circuit. So the laptop lid closure detection. So when you close your laptop lid, it knows it's off because it can have a reed switch in there. Bicycle speedometers can often have these. Proximity sensors, keyboard switches in vintage computers can use these as well. So, some limitations of reed switches. You can see I have a 3D model one there for a project that I'm currently working on. The project's finished, but you'll not get to see about that until Christmas, because it's my Secret Santa gift for Dr. John. So yes, the mechanical contacts wear over time, so because they will open and close, there is a certain number of times that metal can sort of bend and react to the magnet force. So it will wear over time. The contacts bouncing can cause an issue. We'll have a look at code that can potentially get around that later on. There's a limit of physically how fast these things can switch, because it's a metal bending and reacting to a magnetic force. There are sort of limitations, so 100 hertz, 100 times a second, it's pretty fast, but maybe not fast enough for something like a speedometer. Sensitive to shock and vibration. That's obviously in a glass vial as well. That could potentially break. Glass is glass and glass breaks, as Jerry everything says. And yeah, physical size constraints, they are a certain size and they can't really be shrunk down. There's certain limitations to that. Hall effect. Now these are very different. These are solid state electronic sensors. So these can detect the field strength of a magnetic force. So not just that it's kind of on or off, but we can actually detect the amount of force that's that the magnet is putting on this. So that means we can use them to detect the kind of closeness of the magnet. It's named after Edwin Hall. I only learnt that when I was doing the research for the show. I always thought it was something to do with like in audio, when you have like a reverb, you can have like a Hall effect in the reverb, which just means it sounds like a great big hall. And I, for some reason, just thought it was to do with like a physical hall. Not Edwin Hall, 1879. So he discovered the principle that makes these work. I've got a slide on exactly that in a second. No moving parts in these, so they have a much longer lifespan than the reed switches, but they do require power to operate. So they have to be constantly powered for you to be able to read the magnetic field. It's part of the principle that Edwin discovered. So the current flows through the semiconductor. That's what the grey box is there. There's a little electron flying from negative to positive on our little circuit there. If we bring a magnet near it, it will actually deflect that electron and kind of separates them out on that plate that we have. And we can read a value of voltage across the plate, so kind of perpendicular to the flow of the current. So that means that we can detect the amount of current that's being generated by this magnetic field, and therefore the field strength can be detected by the voltage that's being drawn across there. So we can use that. We can do an ADC read on our MicroPython device in a second. We'll have a look at that on the demo. So yeah, no mechanical wear. They can switch much faster than the reed switches, so up into the megahertz, millions of hertz per second. You can measure the field strength, so not just on or off, but how much of the field is being present there, and they're much more reliable and durable. So you can drop them; they're not susceptible to vibration, things like that, and much smaller package sizes are available as well. So these are used in all kinds of applications. So such as motor encoders, they typically use the Hall effect one. The motor speed sensing, so anti-lock brakes, engines, that kind of thing. Position sensing, so on a crankshaft or on a camshaft, you can actually detect where it is by the field strength, if you like. And current sensing, so you can see, is the current present? So you can actually detect if there's current going through a wire. That's how those detectors work when you're sort of trying to find a stud in a wall, and you can see if there's a current going through it. And smartphones, the flip cover detection as well, back when flip phones were cool. I guess you can still buy flip phones now as well. And then reed switches, they're great for simple on-off detection. Battery powered devices that you don't want to constantly have power going through it because it doesn't require power, they're great for that. And any kind of low-cost solution, they're very, very cheap to buy. So I bought a little packet of these from Amazon in this nice little plastic box, and they came in this little bag. So I think I've got about 20 or so of those reed switches. You can see there, they're in that little bag. Well, I've got some hooked up on a breadboard. We're going to have a play with them in a second as well. So let's put those back down there. So, which one do you choose for your project? Well, it really depends on what it is you're building and what kind of sensing that you need there. So reed switches are great when no power is needed or available. You simply just want an on-off switch, and very low cost is a critical aspect of this. If you want a Hall effect sensor, they're great for when you need an analog output, when you have high reliability is required, fast switching is needed, and a digital output is preferred. So yes, we can have all these different aspects. on there. So if you like this, you want me to make more shows about electronic components that you can use in your robotics projects, then definitely drop me a comment. Tell me what kind of components you'd like me to cover next. If you've not liked this video, definitely give this video a like. We always like to see a bit of love on the videos, particularly when it's live streaming as well. I like to see live if this is going down well. And if you've not subscribed to the channel, please consider subscribing. It means so much to me when people subscribe to the channel. So definitely do that if you've not done that to date so far. And I do go live every single Sunday at 7 o'clock. We're in Greenwich Mean Time now. We're in, no longer in daylight savings time, so 7 o'clock GMT. And you can join the live stream, so definitely check out that if you're watching this on replay and you want to join on a Sunday. Great, let's get to a bit of a demo then, shall we? So we're going to look at reed switches and the Hall effect sensors, and we're going to use a Raspberry Pi Pico and some MicroPython as well. So let me just get my stuff sorted over here on the bench, and let me bring up Funny on the screen as well. Oops, I just launched Slack there, didn't mean to do that. Let's just quit that and go into Funny. Right, and the other thing I need to do is get my notes up on this other screen. Great, okay, so let's go over to Funny. So you can ignore all the files that are currently on the Raspberry Pi Pico. These are all the Pico Tamuchibi code, so it just happens to be the Raspberry Pi Pico that I pulled off the desk there, so it doesn't matter what version of MicroPython we're on for this particular demo. So first of all, we're going to look at reed switches. So the first thing we need to do is do from machine import pin. Oops, import pin. Let me just fix why it's doing that. So let's do primary display. Let's see if that works. Let's try secondary display instead. Sorry about that. I just want it to show. There we go. That's better. For some reason it was sort of glitching out. There we go. Import. So we want to import pin. The capital P. And we're also going to import from time import sleep. And we're going to define which pin do we want to use for our reed switch. So let's say reed switch pin equals 0. I'm just using pin 0. Why not? It's the first one. And we're gonna capture what current state it's in and just see if that state changes, because we want to be able to count how many state changes we get. So how often does our magnet connect to it or not? So let's just do a previous state equals, and we need to set up the switch first of all because we've got the switch pin there. So let's say switch equals pin, and it's going to be pin 0, which is our reed switch pin. And we also want to make this a pin.in because it's an import, and we also want to do pin.pullup to use the internal resistor for that. So the previous state is going to be equal to the switch dot value, like so. So if it's a 0 or 1, we're going to store that in previous state, and then we're going to have a while true loop. I'm going to create really basic code, and I'm going to have a look at how to improve that code a little bit later on, but I basically just want to get to the good part first. So let's just say current state equals switch dot value, like so. So that'll read, is it a 1 or a 0, true or false? And then we can say if the current state is not equal to previous state, then do something. So we can basically just print out, let's print out the state is, and then in little curly braces, let's do, I'm using an F string so that I can put in a variable as long as it's in those little curly braces. So let's just do switch dot value, so we can actually see what it is. And let's also have a count thing at the top here, so count equals 0. And we're also, every time we change state, let's increment the state. So let's say count plus equals 1. So it's going to increment that. And let's just add into that string there, and the count is, and then count. Okay, let's run this code and see what happens. So what I'm going to do, I've got on the overhead, let's go to the desk over here, I've got a little circuit here, and currently got two different reed switches set up. Let me just plug this in. Let's go straight to the overhead camera for a second and you can see what's going on here. So I'm going to just plug that into there, not into there. So what's going on here, we've got the grey wire there, which is just going to that side there, and we have another one which is on the ground going to the other side there. So basically we're just going to read as an input what the state of this is. So if we go back over to that kind of shared view, and what we want to watch for is when I bring this cartoonish magnet here close to this reed switch, can we get it to flip its state? So there we go, so the state changed and the count went very high. So whenever the state goes from 1 to a 0, our count is increasing. Now we haven't got any kind of sleep value in there, so let's go back to our code and just in that while true loop, let's just put in a sleep for say 1/4 of a second. And let's also have a statement up here which just prints out what the current value is as well. There we go. Just so we've got like a rolling count of the thing. So if I bring this magnet close now, we should see that it will flip. We get pretty close to it. Let's see how close I can get to that. And we should then see that the count will increase in value. There we go. So whenever the value is changing, we get that high value there. There we go. So that's one example of using this magnet close to this reed switch here. So the other thing I thought would be quite a fun one was if I had a little magnet inside this little circle thing. It's got a little handle on it there, and we've got some little measures there, and there's a little arrow just there which is where the magnet is, and I've simply just got this bolt. We can put that through there, and then I've got another reed switch here, and I've designed this so that the magnet will pass directly over the correct place of the reed switch, and then I've got two crocodile clips there off the back. So if I take those wires off there, it doesn't matter which way round these go. Now let's connect this up. We should now be able to do the same thing with our code. So we go back over to our code. Let's try and bring that up a little bit so that we get, there we go, the very leading edge. So every single time I turn this round and it passes, so whenever that little mark there passes the very bottom, it should tick up. Now you might notice it sometimes ticks up more than one when we go over it, and that's not great. We want it to accurately just change. See there, it's going up many times. Really we want it to just go once as it passes over. So we need a debounce. So one of the issues with reed switches is because it's a physical device, when they're nearly connecting and not quite connecting, you can sometimes get this kind of bounce effect happening. So what I'm going to do now, I'm just going to move that off there as well, to rotate that round, and I've got a slightly better piece of code. So our code here, which is like 21 lines, that's okay, but there's a better version. So let me just go full screen on this code here and show you exactly why this is better. Here we go. So this one is 40 lines, it's twice the number of lines of code. So all this is very similar at the beginning. We've got this last change time, and we have a debounce delay. So how many milliseconds do we want to capture for the debounce? I'm just going to stop that code from running as well. So this introduces like a debounce delay, so we can increase or decrease that delay as we see fit there, as well as storing the previous state. We're going to also capture the previous time in milliseconds. So what we need to do on here then is when we're going to have a try except, just in case we have a keyboard that stops the program from running, and then we have the while true loop. So we're going to capture the current state, whatever the switch dot value is. We're going to capture the current time, so ticks dot millisecond is a way of doing that. Then we have the current state. If the current state is not equal to the previous state like we had before, and if the ticks difference between the current time and the last time is greater than the debounce delay, So we're basically checking to see, are we in that debound zone or are we not? If we're not, then we can then say the current state equals 0, count plus equals 1, so we're incrementing count, and then we're either saying count it, the switch is closed or the switch is open, and updating the previous state, the current state, and the last change time with the current time. And then we've got a really, really small, every 10 milliseconds asleep as well. So let's try this code and see if this is any better at detecting the changes. So let's go back over again to the split screen, and we just move up the window so we can see the output there. And what I'm going to do, I'm going to rotate this round again, and let's see if we can get this to count a bit nicer. So there we go, 7, 8, 9, 10. So it's whenever this is at the top and whenever that's at the bottom. So you can see that it does seem to be counting up in 2s every now and again. That seems to be quite accurate. But obviously we can go quite fast with this as long as it's not 100 times a second. That seems to be the limit on how fast you can read that. So that was quite a fun thing to do, embedding a little magnet in there. That was quite fiddly to design these. I think it's 6.5 or 6.6 millimeters for a 6mm magnet. So the magnet's 6mm and the hole had to be 6.6 for it to fit on my 3D printer. Cool, so that's a fun little thing there that I created just for this demo. And the other thing we have on here is we have a little Hall effect sensor. So I'll just show you these on the overhead camera real close up. So these are really small, they're just like a little 3-legged component. See if I can get that on screen there. So not very much to them. And the wiring is, the middle pin is the ground, and then we have on the right hand side, as the flat face is sort of facing you, we have the 3.3 volts power in, and then on the other side we have the kind of output, so that's another 3.3 volt output, but we can read that as a analog signal. So I've got that one hooked up on the Pico, you can see over here on GPIO pin 26, I think that is, and that's one of the GPIO pins. I think it's GPIO 0, so ADC 0, apologies, on there. And we've got the 3.3 coming out of the pin there, the power pin. I'll show what pin number that is, pin 36 that is, for the output. And then I've just got one of the grounds. I think I'm just borrowing that ground over there. Just might make that out there. Right, so we have our Hall effect sensor. So let's get over back to the to Thonny. Let's create some code for this. I'm going to stop that code running as well. Somebody says the magic smoke's been released on that breadboard at some point. You can see where that might have happened. Well spotted there, Wayne. Right, so let's get back over to our code. So that is that one there. And let me just get my notes open for the Hall effect sensor code. Okay, so similar from before, we're going to say from machine input pin. And we're also going to import ADC, which is our analog to digital converter. Try saying that 2 times fast. So from time import sleep. We always like to use our sleep function. And the Hall, oops, why do I keep putting a bracket on there? I think it's just automatic. So the Hall effect sensor, Hall sensor, let's call this Hall sensor, is on pin 26. So we say ADC, and then we pass in pin, and then we pass pin 26 to that. We don't need to specify an input and our output. They're not really configurable in that way, so it wouldn't work. So we don't need to pull down or pull up. So what we're going to do now is just create a little function that's called read Hall sensor. And we're going to basically just do a number of samples. So let's see, samples is just an empty array, an empty list, and then for, we don't need to store that value, so we can just put a little underscore. We could put I, for example, but we don't need to use the variable in our code. So, and then we're going to take 10 samples, and then samples.append, and then we're going to read in the Hall sensor, and then we use a read 16, so it's a 16, so an unsigned 16-bit integer. Okay, we have to put the little brackets on that, and then let's sleep for 0.001, so that's 1 microsecond between samples, and then we can then return the sum of all those samples, like so. And then we need another function which is convert to voltage. I'm going to take in that ADC value, and we're simply going to return. So let's just give this a bit of a description of what we're doing here. So convert 16-bit ADC value to voltage, and that's between 0 and 3.3 volts. And we can simply just return that value, so return ADC value that's been passed in, oops, and we can divide that by 65,535. That's a 1 byte, and then we can multiply that by 3.3, which is our voltage, and we should get what we're after there. And that we can now print out a little message that just says Hall effect sensor reader, and then like press CTRL plus C to exit. New line. Okay, and let's have a try except block. So this is just a way of capturing that keyboard interrupt. So we'll just say while true, and we're basically gonna oops. So I'm not used to Thon. I tend to code in Visual Studio, so sometimes I press the wrong key on here. So read average value. So raw value equals read Hall sensor, voltage, and then equals convert to voltage, and then we can just put in that raw value that we've captured, and then we can print out an F string. Again, we can put variables in here, so raw equals raw value, and if we do colon 5D, we can specify like how many decimal points we have on there. Yes, as I wonder if the final slide said anyway, that's all folks. I'm wishing I'd put that now. Voltage, and then let's just have voltage, and that can be 3F, oops, .3F, and then volts. There we go, let's have a capital V for that. And then let's just sleep for half a second. And we can just finish off that try except with an except. And we can, this is a keyboard exception that we're looking for, so let's just put that in there as well. So keyboard interrupt, and then we can, oops, and then we can just print program stopped, like so. Okay, let's give this a save and give this a try. Can't import pin. Pin has a capital P. Let's try that. There we go. So we've got the raw value and we have the voltage as well. So currently GPIO pin 26. It does seem to be jumping around quite a bit, which is weird. Okay, we'll stick with it. Let's see what happens if we go now over to here. I've got my comedy magnet that's got our magnets embedded within it. If I bring this really close to the Hall effect sensor, let's see if those raw values change. We get real close to it. So they don't seem to be changing at all at the moment. They do seem to be changing there. There we go. So if I move it away, and then I move it close. If I slowly move away, let's see how effective this is. These magnets are pretty strong as well, so I'm not sure how good they are. I don't know if the direction makes any difference. If I do this top down, I really want the magnetic field to be just in the right spot, but you can see there, if I hold this pretty close, it's about 5mm away there. It drops right down, and if I remove that again, it jumps right up again to that 100 and 200 range. I move it close, if I go to about 1 centimetre, doesn't seem to be affecting it too much. Then I go a bit closer, and it drops right down again. Again, these are average values. We're taking 10 readings and then averaging the sample. So what I'm going to do is just double check on my other code. So I've got 2 lots of code here. Basically the code I just typed out should be exactly the same, but I might have typed a value incorrectly there. So I'm just going to come across with this magnet, try that one there. Yeah, so I'm just going to quickly see what's different in the code. Ah, there we go. So in the code that we just typed up in our demo, in the return samples there, on the sum, I didn't divide it by the number of samples. So if you do length of samples, like so, the double divide just means divide, but don't leave any remainder. So it's a whole number. Let's try that again. That should be a bit better this time. There we go. So it jumps down to almost nothing, the voltage, when we put the magnet close to it. So we've got a working Hall effect sensor there as well. So one of the projects I was thinking of using this for, these over here, a project I've had sat on here for quite some time, and I've not really been sure about the best way to implement this. I was thinking about creating a 3D printed MIDI keyboard. So I've got these keys that I've designed that a bit of an unusual shape to them, and I was thinking about you know, how do we capture the key press? So you could have a simple button underneath there, like a little tack switch. So when you press it, but you would have to definitely press it onto the tack switch each time, and it might musically not quite sound very good because you would be sort of having to make that definite connection with them. On the more advanced keyboards that you have, they are touch sensitive, so they can detect the velocity of the key, so how fast is the key being pressed. So what we could do is put a magnet on each of the keys and have a Hall effect sensor underneath them on a printed circuit board. So as we press them either quickly or slowly, we can have that more nuanced velocity detected rather than it just being kind of a key on or off. So that's one of the projects I've got on the back burner for that. I was thinking about all kinds of shapes of keyboard that we could make with this. Go for like a Max Rebo style rounded keyboard. We could have a complete circle if we wanted to. I don't know, something like that. So that's one of the projects I've had sat on here for some time as I've just been thinking about that. And this was one of the experiments I wanted to work with to understand how do these Hall effect sensors actually work, and can we do something fun with them. So let me know what you think about that. Let me know what kind of projects you'll be putting those into as well. Cool. So that's pretty much the demo that I wanted to show you today. Very simple. The code is available. I'll put a link in the description to that. I don't want to give away what the Secret Santa gift is until Dr. John has received that, and if I put what the actual name of the Git repository where these are all sat is, it might give that away. I'm not sure if I've already done that in perhaps. Cool. So if you want to join our Discord community, we're on the Discord. We have our own KevsRobots group on there, our own server. So go to kevsrobots.com/discord and you can definitely check that out. And there's a new feature on kevsrobots.com that I want to bring your attention to. Let me just load up a browser and get that loaded up, and I'll show you I'll give you a bit of a teaser about what's coming on KevsRobots. Let me just load that up there. Cool. So if I go over to here, let me just remove that. So yes, you might notice over here there's a little login button that's just hidden at the very top of the screen there. And you'll also notice when you scroll down, you've now got these little stats, a bit like on Twitter or social media. So how many people have viewed a particular page? Have people liked that page? Have they left any kind of comments? So we go to this Arduino Uno Q robot. You can see there it's been viewed 185 times, it's been liked 5 times, and there's been a couple of comments on it. So if you scroll down to the bottom of the page, you can have a look and see what's been going on there. So let me just give that a bit of a refresh. Sometimes it doesn't quite work the way I want it to. I'll have to check, because it is quite a new feature. There should be some comments on there that appear. That's what I'm looking to see. So it might be a bit of a bug that I need to fix on there. But yes, once you've logged in, and there's a nice little login screen there. Let me just type in my username and password. You can now like things. So if I've not liked this already, I can hit that little button and it'll increase or decrease the little like count on there. So there you go. And you can leave a comment as well. There we go. So comment's been successfully added. So hopefully when I refresh that, we'll see that. I think there's a bit of a bug there. I need to work out why that's not coming up there. Of course, it's a live demo, so that would happen. But that's a new feature. So what we will see on, let's see if there's another example of a comment that we can just pull up. See if there's one on that gears one there. Let's scroll down. No, it must be a bug. That's really frustrating. I thought I'd got that working for you to see. But yes, you get your little profile icon on there as well. So if I go over here, you can see I've got a little profile picture. You can have a little bit of a bio about who you are. And you can also see there how active you've been on the platform. I've also got an admin panel, being an administrator, so I can go in there and remove people, add people, make them administrators, all that kind of good stuff. So, yep. Pietro says, refresh the page a couple of times, Kevin. I think it might be my browser, actually. Let's load this up in Safari and see if that works any better. Because I've been doing all the development in Chrome, it might well be that it's just like a stuck cookie. So kevsrobots.com. There we go. See Garon there at the bottom of the screen. Right, so let's go to Kev's Robots. Let's go into that Smiles queue and see if there's a comment at the bottom of the screen. There we go. So you go. This is my favorite robot, and you can see as well there's a little edited button. If you press that, you get like previous edits to that comment. So if people say something and then change it, you can actually go in there and see what was previously said. So that's on that Smiles queue robot. And again, I can log in on that one. So you need to be able to be logged in to make a comment on there. I'll be building out the features on Kev's Robots to make it a lot more interactive, and the best place to build robots online. That's really what I'm going for with Kev's Robots. I'm going to bring in user-generated content to be able to put your own blog entries on there, write your own articles, but most importantly, create your own projects and share the code and the build instructions for that. So that's what I want to be building out over the next couple of weeks on there. So I just wanted to show you that just while I remember. And we're talking about all the cool things that is Kev's Robots. There we go. If you want to follow me on social media, I'm on all the different social media platforms. So I'm on obviously kevsrobots.com. We're on Threads at Kevin McAleer at threads.net. I'm on TikTok at Kevin McAleer 6. I'm on Instagram at Kevin McAleer. I'm on X at KevsMac. I'm on Mastodon at KevsMac at mastodon.social. And also on Blue Sky at kevsmac.bsky.social as well. So if you're on any of those platforms, definitely give me a follow and say hi. And if you're working on a project, share a picture of a project that you're working on. I'm always keen to see more robots online. And if you want to follow me in a more financial sense, you can do that as well. You can join the kevsrobots.com Buy Me a Coffee group. So there's a platform for Buy Me a Coffee. You can definitely do that. It reminded me of the impression that I need to do. I'll do that after I've ended the show, Ford. So yes, that's the Roadrunner impression I said I would do just at the beginning of the show. So yes, if you want to do a super thanks or a super chat, you can do that live on the show as well. Bring that up on screen there so I can see what people are talking about. And there's a Buy Me a Coffee page. If you click on, you go to kesrobots.com/coffee, you'll get all the instructions there and you can buy a coffee. A number of people have done that very generously, so you can also do that too. For the price of a coffee, you can support the show financially. And I want to give a shout out to all the people who've done exactly that right now. So let's go over here. And on the left-hand side here, we have all the people who've been on the Buy Me a Coffee side. So Martin bought me 2 coffees in the past month, as Charles Stevenson bought me 3 coffees. Thank you both very much for that. I do enjoy good coffee. We have Pietro, Michael, Warren, Anonymous, Silicon Fiber, Marie TKD, Jeff, DN Corti, Marlin, and Tom. So it's great to see you all on the Buy Me a Coffee side. And then on the YouTube side, we've got a new member. We've got Grandpa Gray has joined the membership. We've got Shrishva, we have Marie, Pete, Dale from Hybrid Robotics, we've got Oxrad39, Warren, Brian, Pieves, Bert, Michael, Steve, Ford, Bello, Johnny, Stephen, John Paul, Cassie, Johnny, and Tom. Sorry for destroying all your names on there. I'm terrible at names. Please carry on supporting the channel, even if I mash up your name. I've had an unusual surname all my life, and people always sort of chew on that when they've not spoken to me before and don't know how to pronounce it. So I feel you on this one. So thank you so much for supporting the channel. It means so much to me that people do that. Very much appreciative of that. Okay, let's get back over to the slides. And the spinny logo tells me it's at this point in the video where YouTube will be recommending another video for you to watch. So over here, YouTube will be recommending another video for you to watch. Definitely check that video out. Let me know in the comments what you think, and I shall see you all next time. So thanks for watching, and I shall see you next time. Bye for now. I shall just hit the stream marker button there. Meep meep. Didn't quite get that one right then. Meep meep. That's my Roadrunner impression. It's really worth waiting for, Ford, isn't it? I like that you kept that in your mind the entire time, though. I used to love Roadrunner. That's one of my favourite cartoons. Grew up watching like Donald Duck and what's he called? The rabbit, whose name escapes me for a second. What's the rabbit called? They always had like a alphabetical alliteration name, didn't they? Why can't I remember? Bugs Bunny, that's the name. Don't know why I couldn't think of that. I think it's because of rabbit. So yes, can you do any impressions there, Ford? Bugs Bunny. That's correct. That's correct. I couldn't remember the name. When you're live streaming, it's like half your brain gets taken out of usage, so you forget stuff. Another cool thing I wanted to sort of show you in the after chat thing there is I've got this Pico controller from Simon Monk Makes. So it's got this really cool little screen on there. That's one of those 128 by 64 pixel displays. There's a whole bunch of little buttons on there as well that are programmable. You put in your Pico in there, and you can then control a whole bunch of relays. So they could be motors, whatever you like, and you've got access to all the GPIO pins. And on the top there, you've got another bunch of pins that you can access. So it's pretty cool. There's even a nice little reset button. I do like it when people build these kind of workshop. The other one that I use a very lot for my projects, probably in my desk over here. So Pimroni did a version of their own called the Explorer, and I use that an awful lot for projects as well. I can't seem to find that right now. I've got another Kibo on there as well. What's that one called? That's the Kibo 2040 Venus Dust. So it's got Raspberry Pi RP2040 in there. But yeah, this one is USB-C connected. But it's not Bluetooth enabled, which is the only thing I thought was missing on that one. Well, I can't find that. There it is. There it is. Hiding. So this is my other favourite board for working on. So you can see the two of them kind of side by side there. So the Monk Makes Pico controller and the Pimroni Pico Explorer underneath. So that's a colour screen. That one is a sort of black and white or on and off kind of screen, much simpler. You've got the Pico there, or the Pico kind of there on this one, and there's also this little breadboard area as well. But you've also got these connectors here for accessing the GPIO pins, and you've also got these breakout garden connectors. So if you have one of the little breakout garden modules, I wonder if I've got one of these to hand here. kind of, but I think. So unfortunately, I've actually soldered something onto the back of this this little breakout garden, but that's one of the breakout gardens. That's a ICM 2948. Anyone know what that is? It's a gyro, compass, and accelerometer. So yeah, if that didn't have the header pins on there, you could basically just push that into the little breakout garden connector there, and it would read that little sensor. So it's a way of like solderless way of trying things out with these little Pimoroni created things. So they're really cool. Yeah, that's a new one that I'm going to try out, which is the Monk Make one. So I'll show you that one. But a little cool project I've got to play with this week. Got a whole bunch of Monk Make stuff. There's another one there which is like, looks like something off Knight Rider or Back to the Future. 7-segment display. That one's designed for a BBC microbit. So you can get your little microbit and connect up the little crocodile clips for that one. Yes, the other thing I've got over here, let's go grab it. I'll be looking at the Ugreen NAS Sync, as they call it. This is a 2-bay diskless. The diskless thing means that it just hasn't got any discs in it. But yeah, I'll be unboxing that one next week. It's currently all in its in the packaging, and I want to film the unboxing of it, so that's going to be pretty cool. I've already got the Ugreen. It's just over there. I go to that view there, just over there behind that, underneath that C3PO that's just there. That's where my NAS collection of NAS drives currently lives, but this one will be up in the house, away from the physical summer house. So should the whole building burn down, I'll be able to have a backup of all the files that I currently store on there, which is all the YouTube videos I'm working on. You won't believe how much drive space YouTube videos take up when you're creating them. So typically I'll have 3 cameras on the go. I use these old mobile phones that I've got. They've got really fantastic cameras on them. I've got 2 of these. One's a iPhone 14 and one's an iPhone 13 and 15. I can't remember. I'm on the 17 now, so it tends to be every 2 years I get a new phone. So I have them on little stands, and they're recording like a left and a right view. You've got the top-down camera recording as well, and then there's if I go to that view there, you can see there's quite a few different views of the desk. Got this little camera here, and we've got the top-down camera over here as well. So I've got a number of different cameras, and I'll have all of them recording at the same time. So it's like 4 or 5 times the number of file size for the video that's coming in. I'll be filming on the main camera as well, and I might even have my other camera, my new phone camera, recording as well for some other stuff, because this has got a fantastic camera on it as well. And you can use on the iPad, there's a Final Cut camera app that will do multi-camera. It'll take all those views, it'll put them all together, and then when you're editing you can very quickly switch between the different cameras just from one view. It's really, really neat, but it does take up an awful lot of space, so having all these NAS drives for a YouTuber is absolutely essential. Cool. Was that the impression that was amazing on the demonstration? Meep meep. Can do better when I've been practicing the Woody Woodpecker impression. Cool. Cool. So yes, it is a gyro. Well done, Ford. You guessed that right. So yes, Ugreen Gizmo test. So what I'm looking to do with these is have like a backup NAS and use the Ugreen software. It's called UGOS Pro, and it's basically like Linux, and it's got a really nice suite of features in there. Specifically designed for backing up stuff, but you can synchronize your backups between 2 devices even if they're really remote. So that's exactly what I'm looking at doing there. This can have this one as like a satellite. So Ugreen, they've even provided a bunch of hard drives as well. Try and grab these. In a really nice little box. Oops. So 2 4TB drives in there, so they're Iron Wolf, Seagate Iron Wolf drives, designed specifically for NAS usage. So not the fastest of drives, but they are decently sized. So that's really cool. That's what I'll be working on probably tomorrow, as well as some other projects that I've got going on. So tell me about what projects you're working on at the moment. Is there anything that you've got on the go? I've been meaning to build another project, another robot project, a much larger project. And one of the things that I'm kind of procrastinating about is what material should I make the base out of? Should it be like a 20 by 20 aluminium extruded bar, kind of surround? Should it be 3D printed? There's kind of size limitations with 3D printing, but I could make it so that there's a number of pieces that kind of bolt together. They do take a while to print, but again, I've got plenty of time. I could print those out and have like a really big robot. I've got a bunch of quite chunky wheels that I've got encoders, so I was thinking about making kind of a wheeled robot, but I could also go for a tank track driven kind of robot. Don't know, thinking about you know, what options we've got there. So yeah, another one says, hope the drive serial numbers are from different batches. So tell me about why that is. Why would you hope they are from different batches? Is that so that gives you a bit of like the mean time between failure will hopefully be a bit different between the two drives? Typically, the drives I find last about 10 years. I've been in IT for like 30 years, so I've kind of seen the life cycle of SATA drives quite a lot. I built quite a few NAS solutions myself. I've got 2 of them underneath my desk right now. So I've got a true NAS. Well, let's see if I can bring that up actually. I've got a true NAS box. I keep all my IP addresses in Obsidian so I can find the IPs really easily. I do tend to have them on static, so that they don't change when the router reboots. So let me just find on here. So I'm just looking up where the machines are. So servers, there we go. If I go for TrueNAS, there we go. That's the IP I'm looking for. Let's bang that in. So I've got a TrueNAS core. What's my username? I have absolutely no idea. Is it Kev? Is it admin? Is it some combination of that? I can't remember my password now. I would have guessed it'd be Kev. Let's try lowercase Kev. Never going to get those files back, am I? Let's try that instead. Is it root? Root. There we go. So yeah, this has got this is all solid state SSD drives. So I think I bought 5 1TB drives back in the day. I'm sure we can go to storage on here and have a look how that's configured. Disks, that's the one I'm looking for. Oops, storage, disks. Yeah, there we go. 5 1TB SSD drives. So yeah, they're quite expensive to buy. About 5 years ago when I bought these, and it's really fast, but I've not really got fast networking in here. It's like 100 gigabit, which is usually fast enough for people, but if you're doing like large file transfers, you need something a bit more beefy than that. Yeah, another one says, when we build big storage, we split serial batches between units. Interesting. Hey, not you, not me. Not you, not me, from Brisbane. How's it going? Yeah, Eve says, thanks again for a great show. Got to attend Family Matters. Have a great week, everyone. No problem. My fat self thought of the sandwich when I heard gyro. Ooh, you green gizmo test. Cool. So what else? Yeah, lower mean time between failure risk. Yeah, cool. That's good to know. What else was I going to say about... so that is my TrueNAS one. I also have a Raspberry Pi base drive. We did the Snazzy NAS a while ago, if you remember. Just jump back to me for a second while I find on my Obsidian. If I've got that one up. I don't think it's that number there. Let's see if I've got it on nodes. No, I've not got that one to hand, but I have a backup NAS. If I go to Quick Connect and I also go to Ugreen Link, let me just bring up both of these. So I've got this Synology NAS which I bought out of my own pocket before I got sent all these nice freebies from Ugreen, and the Synology one, I think it's a 2022 model. It'll pop up in a second, and I've got the Ugreen DXP 4800 Plus. So I think I'm Kev on them ones. I can never remember my password on these things. I think I'm Kev on that one. Alright. So I think it'll be the same kind of password on that. There we go. So yes, on these ones, let's go to control panel. Let's go to I'm trying to find the storage thing. Maybe it's not on there. Maybe it's a separate one. Storage manager. There we go. Yeah, they look very similar. The interfaces for both of these as well. So does that not log me in? So on this one, I've got 3 drives, and these 3 drives, if we go to there, these are 14.6 terabyte. I'm sure they were branded as like 16 terabyte drives, but 14.6 terabyte, 3 of them. They're all in a RAID configuration, so you effectively get like the 28 gig before you put the file system on it, if you like, because one of them is a parity. And I've also got half a terabyte SSD for cache, so that just makes the drive a bit quicker. Does somebody give me a thumbs down then? What's the thumbs down for? Let me know what you disapprove of. Let me just try that again. Let me know in the comments what you disapprove of. So yeah, that's the setup of that, and there's some really nice software on here for backing up and doing kind of a scheduled backups. So it's called Hyper Backup, and I've got a number of different shared folders on there. So you can see you've got code, Docker, downloads, family, photos, VM, videos, and work. And there's also a Ugreen work backup, so that will back up anything from the work one to the Ugreen one as well. And they're on kind of a schedule, and it will keep them for a certain amount of time before it recycles them. I think it's about 2 weeks, something like that. So that's pretty good. It's still not letting me on this one, is it? What if I put as the password? I thought they had the same password. I must have been really secure and used different passwords on these ones. But yeah, the Ugreen one looks exactly the same, to be honest. Let's try Kev with a capital K, just in case it's case sensitive. There we go. We're in. So this one looks very similar to the Synology. We look between the two of them, and we have a similar kind of thing. So we've got storage. So I've got 2 hard drives attached to this one. Oh, 4 hard drives. So I've got 2 4 terabyte drives and 2 1 terabyte drives. I'm not currently using those. So the two basically just mirrored at the moment. But because they're using BTFRS, we can actually add an extra drive of the same size and then extend it, and it'll shuffle around all the different blocks in there to make sure that the drive has proper redundancy. So it's pretty cool that you can do that. So this BTFRS, BetterFS. So that's the kind of configuration I've got on that one. And you get all kind of apps on both of these. One of the cool apps on this one is you can have virtual machines, and you can actually run Windows 11. So I've got a Windows 11 virtual machine just sat there, should I need to have access to that, because I'm pretty much a Linux and Mac user day to day. So do you have a NAS? Let me know in the comments if you has a NAS or not. So what was that there? Is this a snake? Is what a snake? A snake. I'm not sure. Oh, is that the yes, the tongue thing. It's supposed to be the MicroPython logo, I think. So yeah, it is kind of a snake. Cool. I think that's everything I wanted to cover off with you guys this week. So yes, I'll be working on more of the KevRobots.com features. Excuse me, I'm not sure why we had those issues with the comments. Really frustrating that that didn't work when I wanted to show you guys the comments working. But it'll probably be something I just... And now that I want to sort of sign off, the comments feature is now working. I just need to hit the refresh. So you can see there, you get your little profile thing, you get your little profile thing. You can even do @ mentions, so it'll highlight in blue, and you can click on that, and it goes to the person's kind of public profile. So if I go to Pirto's public profile there we go. So Switzerland, joined October 2025. So if you join kevsrobots.com, again it's completely free. If you join that this month, you'll get a special badge as a founding member, and if you help me test any of this as well, you'll also get an extra badge for testing. So it's definitely in your interest to help me get this working and build out more features. You can even suggest features as well. That'll be something I'll be definitely wanting to look at, what kind of features people would like on there. So I'm thinking it's kind of like a printables or Thingiverse, but for robotics, or an Instructables, but it's designed for people who are building robots. So what kind of things do people want to share? What kind of things do people want to see feature-wise on the website? And it'll all be free as well for you to use. So definitely something we want to stick around and help me build. Cool, great, thanks everybody for watching this week, and I shall see you all next time. Bye for now.